Hello students, your professor Dr. Mink. Welcome to another exciting lecture for CompSci 2, CSC 223. The topic at hand is searching and sorting. We'll be covering the contents for Chapter 18 from your textbook Java Foundations. Let's get started. In this chapter, we'll start off with a comparison of the linear search and the binary search algorithms. We will then proceed into the sorting algorithms, including selection, insertion, bubble, quick, merge. We'll discuss, analyze the complexity of the search and sort algorithms, and finish up with comparators. Start off with some terminology. Searching is the process of locating the target element. You'll see that term used quite frequently among a group of items, which is the search pool, or if we don't find it, reporting back that it is not the target element, does not exist within the search pool. Searching requires repetitively comparing the target to candidates elements in the search pool. And an efficient search algorithm performs no more comparisons than is necessary. We're going to define the search algorithms so that they can search any set of objects. Therefore, we'll search objects that implement the comparable interface. If you recall, within that interface, we have the compare to method that returns an integer specifying the relationship between two objects. And here we have object 1 calling compare to and passing object 2 as a parameter. And it will return a number less than, equal to, or greater than 0 if obj1 is less than, equal to, or greater than obj2 respectively. As you probably recall, a class that works on a generic type has to be instantiated. And since our methods will be static, we'll define each method to be a generic method. Generic method header contains a generic type before the return type of the method. And here is an example of a generic method header for the linear search algorithm. The generic data type can be used in the method body, the parameter list, the return type, etc. And here is an example of generic method. On to our first search algorithm is the linear search. The linear search searches or examines each item in the search pool one at a time until the target is found or until the pool is exhausted. This linear search does not assume the items in the search pool are in any particular order, i.e. sorted. And it really doesn't matter if they are sorted. It's not going to cause this to have any problems. It's going to work whether they're sorted or not. Here we have a method named linear search that performs, you guessed it, a linear search. It's pretty straightforward. We pass an array of whatever data we have, and the integer minimum, maximum, which correspond to the minimum index, obviously 0, and the maximum index, And then we pass the generic element t target. And we'll use, I have a a program we'll use next that uses an integer, a string array. But in this case, let's just take a look at the algorithm. So we have int index equals min, Boolean found equals false. And this obviously returns a Boolean, true or false, whether or not it finds the target. And while not found and index less than or equal to max, found equals data index dot equals target. And then it increments index. And it will just walk through every element in the array until it finds the target or finds the end. And if it finds the target, it returns true. If it doesn't find the target, obviously it's going to return false. So actually, yeah, Boolean starts off at false. So pretty straightforward. Let's take a look at a coded solution. I'll put some breakpoints in there. We can actually walk through the search. You have this file in Canvas. I just happen to throw a main right into this searching class. It has two methods, linear search, which I just showed you, and the binary search, which we're going to show you next. But let's take a look at what I've done. So I've declared an array of strings. Its name is names, and this is an unsorted array. You can see there's no particular order, and I'll do it next, sort it. And so we're simply going to look for the string or the name Alice from 0 to 5. We'll call linear search, and then we'll print out found. If it's found, if it's not, we'll print out not found. So I have a breakpoint in the method, in the linear search method. Let's walk through this. So here we are. Let's take a look at our variables. There's our data array, and the names, min is 0, max is 5, the target is the string Alice, index is currently 0, and found is false. So we'll actually walk through this. So I can get this all on one screen. I'll actually walk through this. Okay. Index is now 1, found is still false. So we're now going to inspect Mary compared to Alice, still false, 3, 4. So we're going to have to go all the way through this array. And there we get to target, found. So that walked through every element in the array. Now let's try this differently. I think if I did this right, still have, okay. Now I have the same names, but I have them sorted. So we made 6 passes on this array with the linear search, starting from 0 until we found it, and we happen to have it last. Now, if we run it again, and I'll put my variables here. Okay, so we're at 0, index 0, false, index goes to 1. Okay, and now we're going to find it. We're up here. Found is now true. Return found. There we go. So with the linear search algorithm and the names in, let me see, sorted ascending order, we found it right away. Now I want you to remember this because we're going to do this both ways. We're going to do this using the last element in the sorted array with a binary search, which we're going to cover next. If the search pool is sorted, we have the opportunity to search more efficiently than with the linear search. We can use a binary search. The binary search eliminates large parts of the search pool with each comparison, and it uses a recursive call. Instead of starting the search at one end, we begin in the middle. So just think about this. Now remember, it's sorted. So the element at index 0 is, let's just assume it's sorted ascending, is less than the next element at 1, which is less than 2, right? So we begin in the middle, and we compare the middle to the target. And if the target isn't found, we know if it's in the pool at all, it's in one half or the other. So we can then jump to the middle of the half that contains it and continue similarly. You probably see where this is going. If you don't, hang on. So recall, we're going to implement the comparable interface, which provides us the access to the compare to method. And that'll tell us when we compare it to the midpoint whether the target is greater than, equal to, or less than the midpoint using compare to. If it's greater than, if the target is greater than the midpoint, then we're going to jump to the second half. And in this diagram, it's going to be the half to the right. If it's less than, we'll jump to the half, or the midpoint of the half to the left. Let me walk you through a manual example or simulation of binary search using the sorted list of numbers you see in front of you, 8, 15, 22, etc., up to 88. And we'll say that the target is 29. So we find the midpoint. We'll take the number, divided by the number of elements divided by 2. And if we don't get right in the middle, we'll just go one less. So we'll get to the midpoint of 54 in this list. And we'll compare the target 29 to 54. Well, we know they're not equal. So if it's in the list, we don't know it's in the list at this point in time. And we do, but the algorithm hasn't proven that yet. So we know that 29 is less than 54. So we can eliminate inspection of 55, 61, 70, 73, 88. So we've already eliminated inspection of half of the elements. So then we go to the midpoint from 0 to the midpoint, which was 54. And let me see where that's going to be. So the new midpoint is going to be 22. 29 is not equal to 22, but it's greater than. So now we're going to go to the new midpoint of the remainder between 22 and 54, and that's going to be 29. Because it's not an odd number, we're going to go one less. And that's just luck of the draw. Um, so let's take a further look. We often implement the binary search algorithm recursively, and each recursive call searches a smaller portion of the search pool. And the base case is when there are no more viable candidates, at which point there may be, at any point there may be two middle values, and I've already mentioned this, in which case we use the first. So if there's an even number of elements and you don't get to an exact midpoint, you go to the one to the left. I'm assuming we're talking ascending. We're going to see this, by the way, so don't panic if you're having a difficult time visualizing that at this point. Don't worry, I'm going to demonstrate this live in NetBeans, but I just want to walk you through the binary search method. Uses a generic T, which extends comparable, and we have it returns a Boolean, and we have the parameters data, the generic array of data, int min, int max, and then the generic target. Boolean found equals false, the same as linear search. And then we calculate the midpoint. We take the min and the max and divide them by 2. It's integer division, so we're going to get if it's an even number, we'll get if it's a decimal, we'll get the lower of the two. Then if data midpoint dot compare to target is equivalent to 0, we found it. Else, if data midpoint dot compare to target is greater than 0, right? If the min is less than or equal to midpoint minus 1, found equals, and we call binary search data min midpoint minus 1 target. Else, midpoint plus 1 less than or equal to max, found equals binary. So here's the recursive call again. We call it data midpoint plus 1 to max target. Let's see this in action. Let's take a look at the binary search. I have an array of strings named names, and they are in ascending sorted order. Aaron, Alice, Karen, Mary, Stephen, William. And we're going to search for Stephen. So what it's going to do is, this is 0, this is 5. It's going to 0 plus 5 divided by 2 will be 2.5, but it's integer division. Sorry, I've been doing this all day. Integer division. So it's going to be 0, 1, 2, not 2.5 as the midpoint. Let's watch. Bug it. Here we are. Look at our variables. Min 0, midpoint 2, max 5. Data at midpoint is Karen. You can see that. Data.midpoint.compare to target is -8. Karen is going to be less than Stephen, so it's going to return a negative number. So that tells us that the target is to the right of the midpoint. We'll check to see that if it's greater than 0, that's going to be false. So then it's going to check if it knows that it's to the right. If that's false, it knows to the right. So if midpoint plus 1, let's look at midpoint again. Midpoint is 2. 2 plus 1 is 3. If 3 is less than or equal to max, we still have some items between the new set, right? The new set. Now let's take a look at this. We're now going to search. We determined Karen was not equal and that Stephen was to the right of Karen. So now we're going to search Mary, Stephen, and William, because this is midpoint. Mary's going to be midpoint plus 1. So found equals binary search data midpoint plus 1 to the max, 3 to 5, target. So we're now going to recurse. A recursive call binary search. Here we go. Just so you can see this, you can see the environments. You can see the environments loading up. So now, well, we're in a new environment, and min is 3, max is 5, midpoint is 4. Data.midpoint is Stephen. So we're going to find it this time. There we go. Found equals true. We're done. Return found. And our output is found. You want to try it again? We could try, let me see. We'll try searching for Aaron. I'll use the breakpoints. Now, when the element being found or being targeted is at the end, you get the longest runtime. It's most efficient when it finds it in the middle. So here we are. Let's see what we have. Whoops. Okay. Midpoint 2. Data.midpoint is Karen. Compare Karen to Aaron. We're going to get a positive number, right? It's going to return a positive number, which means the target is to the left of Karen. So watch what happens. Okay. If greater than 0 it is, we'll drop in here. If the min is less than or equal to midpoint minus 1, so if there's more than 2 items there, right? Because the min was 2, and min's going to be 1. I'm sorry, midpoint was 2, it's now going to be 1. So we're going to go from 0 to 1, and we then pass min and midpoint. Here we go. We recursively call that. We're going from min 0, max 1, midpoint 0. Data.midpoint, guess what? It's Aaron. There we go. Ta-da, we found it. Now, obviously, I need you to take these files, which I'm putting in Canvas, download them, put the driver main method in there, and play around with this. You really need to understand how this works. Thanks for watching. Let's compare the search algorithms we just looked at. The anticipated case for finding an element using a linear search is n divided by 2, which is O of n. The worst case is also of n. The worst case for binary search is log 2n divided by 2. Comparisons are made, which makes the binary search O of log n. Keep in mind, for the binary search to work, the elements must already be sorted. Hey, did someone mention the word sorting? Now, if you're in this class, that means you passed several prerequisites. And you're saying, what is sorting? You missed the train. This should be review. When you sort a collection of elements, you arrange them in some defined order based on particular criteria. If they are numeric, they could be sorted ascending, which means lowest, smallest to largest, or descending, largest to smallest. There's also alphabetical. There's all kinds of ways to sort. You can sort strings based upon Unicode values. Many sorting algorithms are in existence. The sequential sorts require approximately n squared comparisons to sort n elements. Logarithmic sorts typically require n logs of 2n comparisons to sort n elements. So what we're going to do is we're going to define a generic sorting problem that any of the sorting algorithms could solve. And in order to be able to sort your elements, we must be able to compare one element to another.
Before we start looking at the individual sorting algorithms, I'd like to show you the contact class. We're going to be using this as part of our demonstration to sort a series of phone contacts. This class, contact, implements comparable for contacts, which means every element in this class can be, every object in this class can be sorted with the compare to method. And all we really have is for our data, we have first name, last name, and phone. And they're all strings. Pretty straightforward. Continuing where we left off, well, let me just say, you're going to have access to these files. I'm putting them in the timeline of Canvas. So, and I'm going to have a live demo coming up shortly. We've got the toString method, which returns last name, comma, space, first name, comma, tab, and then the phone number. We have the compare to method. And I think that may be it, but I think I have one more slide before we get into the selection sort. Yes, we have the public class sort phone list, which is the driver program, and it contains the main. We're going to create an array of new contacts, and here they are. There's going to be 7 contacts. They're in no particular order, and then we will use this to call the various sort algorithms, or sort methods, I should say, in the sorting class, which has, I don't know, 4 or 5 different sorting algorithms implemented as methods. First up is the selection sort. If you had me for the first course in our computer science sequence, this is review. We cover the selection sort and the bubble sort at a minimum in chapter 7 arrays, I believe. So the selection sort orders a list of values by repetitively putting a particular value into its final position. So what it does is it finds the smallest value in the list and it moves it, it switches it actually, swaps it with the value in the first position in the example we're going to be using, because we're using an array as the list. It's going to be index 0. And then it'll search the rest. It ignores index 0, and then it'll sort or search the rest of the list for the next smallest value, put it into index 1, step ahead, and it'll repeat until all values are in their proper places. It's in many ways the opposite of the bubble sort. So if we had a list of integers as depicted in this slide, and 3 is in the first position in the list, 9, 6, 1, and 2, we will begin the selection sort by scanning right with 3 as the element we're comparing to everything else, and it will determine that 1 is smaller than 3. So it will swap 1 and 3. Then it will start with the second element in the list, 9. Compare that, and it will determine that compared to 9, 2 is the smallest element in the list. And it'll swap 9 and 2, and then it will start with 6. The 3 will be the smallest element to the right of 6. It'll swap 3 and 6. Then it'll start with 6, and it will realize that there's nothing left to exchange. Live demo coming up shortly, but in the live demo, I have all of the sorting algorithms implement in a single class file called sorting, and they're all methods, and we're just going to call them. So here we break away with the selection sort algorithm. As you see here, we've got, and T extends comparable T, that's the generic data type. And we have an array of generic elements named data in the parameter, int min, T temp, and you'll see that we call another method swap. If you, once again, if you had me in an earlier class, we've implemented this, albeit probably in C++. So we set the index, we have for loop, we set the index to min, and then we scan it, index +1 to less than data length, and if data subscan compared to data min, and we set min to first, it's less than 0, we swap them. I'm sorry, scan equals min, and then we swap min and index. You're going to see this in action. Here, let's take a quick look at the swap method. It's simply swaps, takes a temp and swaps the two. We've covered this extensively, and I'd be shocked if any of you are sitting here not having been exposed to this previously in our curriculum. So let's get on to the live demo. Now we'll take a look at the live demo for selection sort. I've doctored up a little bit. Hey, I've changed a insertion sort. Changing it to selection sort. Here we have, the friends contacts, and we've added 7 contacts. And this sort algorithm is going to sort them by last name, alphabetical ascending. And you can actually see that. So I'll walk you through it. There's no recursion on this one. It's just a simple linear scan through the elements multiple times. I have a couple breakpoints. So here we are. And what I've done is I've printed the entire list prior to it being sorted. So you can see that in the output. John Smith, Marcia Grant, and you'll see there's 2 Smiths, Larry and John. And it does incorporate first names if last names are the same. So let's step into this. So here we are in the selection sort, and we've passed the array, and we've got a for loop. We've got min and temp. For loop starts at 0, lesson, data length -1, index +1. We set min as the index for each one of these, because min is going to increase. So for scan index, we'll start at 0 +1. So we're going to start at 1, scan to data length, scan ++. If scan compared to data min is less than 0, min equals scan. Otherwise, we swap min and index. So if I step into this, here we are into compare to. It's important that you see this method. If last name equals other last name, result equals first name dot compared to other first name. If the last names are the same, then we're going to compare the first names. Else, we'll go on with the compare to last names, and it's going to return that in. Compare to is part of the comparable class. So you know how that works. So let me see here. Right, last name's going to work. We're going to return that, and we're not going to swap them. And we'll just continue, and you'll see it's not going to swap Smith, the first one, until it gets to someone else. So let's see what we have here. Okay, so right now, min is 1, index is 0. So, whoops. Our min is Sarah Barnes. It's going to continue to go until it finds something lower than Sarah Barnes, or until it gets to the end of the list. And if it does, it swap Sarah Barnes into index 0. And it'll just keep going. And eventually, you'll see Sarah Barnes in 0. You'll see Laura Getz in 1. And you see it's still not sorted. I can continue. Or I can just is. Okay, so that's a new min. Is Barnes less than Riley? Yes, so Barnes stays the new min. Is Barnes less than Getz? Yes, it stays. So Barnes, the first pass through, Barnes is then swapped with Smith. Smith is compared to Riley, QRS. Riley's less than Smith, so Riley's the new min. Getz is less than Riley, so Getz is the new min. Getz is less than that, Getz is less than that. GE is less than GR, so then Getz winds up there. Then we go to the third. I think Riley was third. So you get the idea. Now, of course, you have these files. It's really important that you download them, you run them, and we'll talk about which one is more efficient as we move forward. Let's now get on to the next algorithm. The insertion sort is up next. It orders values by repetitively inserting a particular value into an already sorted subset of the list. So think about or consider the first item to be sorted as a sublist of length 1. Done. Insert the second item into the sorted sublist, shifting the first item if we have to. So then we have a sublist of 2. Insert the third item into the sorted sublist, shifting the others as needed. We've got a sublist of 3 that's sorted. You repeat until all values have been inserted into their proper positions, and the sublist is then the same length as the total list to be sorted. Here's a diagram showing the insertion sort for a list of 5 integers, 3, 9, 6, 1, 2. So start off with the sublist of 1 and 3. Okay. Obviously you don't shift anything. So we insert 9, and then 3 and 9 are sorted. So we shift to the right and we insert 6. Then 3, 6, 9 are sorted. Shift 9, 6, and 3 to the right 1, insert 1. Then 1, 3, 6, and 9 are sorted. We shift 9, 6, and 3 to the right, and we insert 2, and continue the process. Here we are in the insertion sort, and instead of me walking you through this with a breakpoint, because it would take a lot of clicks, and I'm sure you could do this on your own. What I've done here is just so that you can see the movement of the elements is I've each time this while loop, this for loop, we start at index 1 and then we look back 1 and we go to data length. Each time this moves, what I've done is I've put a series of print statements. I print out the key, I print out the index, and then I print out the entire array of data. Oh, and I print a new line. So if I run this, you're going to see each time, here I will put a breakpoint here for you. You're going to see each time this runs. Now let me just make sure I don't have any breakpoints anywhere else. I was fooling around with this trying to determine the best way to demo this for you. No, I think that's it. So oh, I do have another breakpoint. Okay. So first time I run this, I hit fast forward twice. Sorry. So here's your unsorted list, and here's the first run through that for loop. The key is Sarah Barnes, right? Because we go from 0 to 1. she becomes the key. And then we'll move Sarah Barnes into the lowest position of the sub list. And then we'll expand the sub list to include Mark Riley. He'll be the key, and we'll move Mark Riley into the smallest, Mark Riley, we'll move him into the smallest or the lowest position he should be in. And then if I continue, then Laura Getz becomes the key, and we'll move her down, and we'll just continue to do this, right? Larry Smith becomes the key, and then Frank Phelps becomes the key, and Grant Marshall becomes the key, and then we're done. So, I mean, that would have taken 500 clicks to get you to this point with breakpoints inside the method. So I'm going to ask you to download those files. Here's what I did. I'll let you take a look at it. Just put a tracer within. Here's what I did to trace that and where I put it. And each time it'll print out the new subset or sublist sorted and the key. Next sort algorithm on the agenda is the bubble sort. I spend time in CSC 121 describing the bubble sort in great detail. We use it to sort an array. So the bubble sort takes an entire pass through a list, starting with the first element and comparing it to the second element. And if it's larger, let's say we're sorting ascending, because you could do this either way, ascending. If it's larger than the second element, it swaps them. And then it takes the second and the third element, and if the second element's larger, it swaps them. If it doesn't, it takes the third element and fourth element, and if it's larger, it swaps them. And eventually, the largest number, assuming we're going in ascending order, the largest value, I should say, the largest element, because they have to be comparable, largest element winds up in the last, let's just assume we're using an array, the last index location. And then we shorten the list by 1, because that highest number is in the last index location. So we shorten the list by 1, thus excluding the last element. And we do the same thing. And we continue to do that till we get down to the last 2 elements. And the entire list will be sorted. You can also do that by simply flipping greater than and less than, and it will bubble up the lowest number to the highest index location, or the last location in the list. And that will give you a descending sort. Here is the bubble sort method used with the generic data type T. So we'll use the bubble sort to sort an array of whatever generic type T data is. So we have our int, position, and scan. T is temp. And so we have an outer loop which starts at, sets position to data length -1, which will be, in an array, it'll be the highest index location. Goes till position is greater than or equal to 0, and it subtracts 1 each time. So this is the structure within this method that shortens the list by 1 each time. So the first time we go all the way to the end, and we move either the largest or the smallest, depending whether we're going ascending or descending into that position. And then the inner loop does the scanning. So we're going to scan from 0 to less than or equal to position, and I'm sorry, position minus 1. You'll see, because we're going to go +1, and we do not want to get an array index out of range. I'm going to run this in the IDE in a second, so not a second, minute, whenever I get to it, sorry. So if data subscan compared to data subscan +1, that is looking at the element and the element next to it. If it's, in this case, we're setting this up for ascending order, it'll swap them, and we've already seen the swap method. So let's take a look at this live right now. Okay, now we're going to take a look at the bubble sort in action. I have the same array of contact objects, and I'm adding those in the order you see in front of you. Obviously they are not sorted. We'll call the bubble sort. And let's take a look at the bubble sort method. I started to run this, and we are in at a breakpoint. So the outer loop, as you can see, decreases the size of the list being sorted, and the inner loop does the work. It compares, it sorts from 0 to the position, which is the size set by the outer loop. So the outer loop just decreases position by 1 each time. And so if data.scan compared to data.scan +1, that's if the element, and for the first run through, it's going to be data sub 0 compared to data sub 1. It's greater than 0. We're going to call the swap method. And I put a watch point, or I'm sorry, I put a watch on data scan +1, and data scan +1 right now, before we step into this, is Sarah Barnes, and a data scan is John Smith. So 0, John Smith is at 0. Let's look back. There's John Smith at 0, and there's Sarah Barnes at 1. So if data sub 0 when compared to data sub 1 is greater than 1, well, Smith is going to be greater, so they're going to swap. There you go. We're going to swap them. And so scan is still 0. So data scan sub 1 is John Smith now, and Sarah Barnes. So John Smith has bubbled up. Now we're going to compare. If I step in, whoops, scan goes to 1. So we'll now, data sub scan is 1, which is going to be John Smith. And the next one, data sub scan 1 +1, which will be data sub 2, is going to be Mark Riley. Is Smith greater than Riley? It is. So we're going to swap them. And now if I look at them, data sub scan, which is 1, is, oops, Mark Riley, and 1 + 1, data sub 2 is John Smith. So he's bubbling up. John Smith is bubbling up. And if I continue, you'll see now position goes to 5, and let's see what data looks like after position goes to 5. I'm sorry, I think I want a position to go to 4. Yes. Here we are. So if we take a look at this now, you'll see Sarah's first, but we're most interested in Larry Smith having bubbled up, and John Smith would have bubbled up until it bumped into Larry Smith, and the last names are the same, but Larry is greater than John because L is after J, so Larry will bubble all the way up. And if we just keep running this, I can remove these breakpoints, and we could just run this and see the output. There you go. They will bubble up. I believe your programming project number 1 for this section is programming project 18.1, which requires you to modify this bubble sort algorithm so that it doesn't take passes after it's sorted, because this will continue to sort even if it's fully sorted to begin with. It will continue to pass all the way from position, in this case it was position 5 to position 1. And those passes are unnecessary, so there's unnecessary computing resources allocated to irrelevant instructions. So take a look at programming project 18.1. I've also asked you to put a tracer or two in there, and you can't use a break statement. So if you have any questions on this, obviously download the files and run them. If you're concerned or you're unsure about any of this, ping me. We'll get together and I'll help you. Next up is quick sort. The quick sort partitions a list around one element. Then it sorts, it places all elements less than, if we're doing ascending, less than on one side and greater than on another side. And it will apply the quick sort algorithm recursively to both partitions less than or greater than. Obviously, we're going to take a look at that now. I've spent a significant amount of time setting up this demo, trying different ways to represent the quick sort and the recursive nature of quick sort. It's not easy. Hopefully you watch those two videos where there's diagrams where that actually shows you the partitions and the recursive calls on the left and right of the partition. This is going to do that, but I had to put some tracers in there. So each time we call, we're going to have this phone list, and it's the same one we've been using, and it's not sorted in any way, and we're going to call the quick sort. And as I mentioned, I put some tracers, some output statements, and I've also put a breakpoint each time it calls itself recursively. So you'll see the environment stacking up, or the calls on the system stack. So what we're going to do is each time we declare a new index of the partition, I'm going to output the new partition, and then before we sort to the left, right, from the min to the index of the partition -1, I'll output sort to the left, and then it tries to sort to the right. We'll output the partition and sort to the right. Now remember, It only does this if the min is less than max. When you get down to a sublist, keeps breaking the list into sublist and then breaking the sublist into sublist. When the min equals the max, which means you get down to 1, that means it's sorted. That sublist is sorted, and it returns, and that pops off the stack. So what I'm going to do is I'm going to run this just so you can see it. I'll run it in debug mode, and when we get to the first breakpoint, you can see, okay, original quick sort was called by main, and then it called itself, and you'll see the environment stack up as I just continue to let it go through. And you're seeing the output. I'm not going to show you the variables because it's very complex. You're seeing the output stack up, and you'll continue until they start to get down to a sublist of 1. And then you'll see them start to pop off. Now let's take a look at the output, and you'll see why I put all these tracers in here. There was a significant amount of recursion. So the initial call from main to quicksort, here's the list initially. And then the current partition, it picks right in the middle, and it will sort to the left. So it will take everything in the list that is less than that last name gets. We actually have 2 Smiths, but then it reverts, then it checks the first name. So you can see that it looks like Barnes is only on the left. So here after that, and then it will call with the same partition to the right, and it will put everything to the right of gets. But that partition is more than 1 element. So it'll split that in half. So it'll recursively call itself with that sublist as the list. And Larry Smith, it'll pick right in the middle. Larry Smith will be the partition. Then it'll try to sort to the left. And it will put everything to the left of Larry Smith. Well, everything in the list goes to the left of Larry Smith. And it will try and sort. So it will pick the middle of that list, John Smith, sort to the left, and it will move everything to the left of John Smith. But that'll be a list that has these names. Pick a new partition, sort to the left of that partition, and then it'll sort to the right because it'll be names, it'll be more than 1 on the right, and it keeps on going and going. I mean, I could sit here and talk for an hour, but you can watch all the iterations of this until it gets to the end. Let me see if I could get this. Oh, darn. And here is the final sorted list. Now, to show this with breakpoints in the environments and the variables is going to take more time than I wish to place or to use in a live demo. So I'm going to ask you to please download this file, put the tracers in, and make sure you understand how this works. It's an extremely important recursive algorithm. Next up, the merge sort. The merge sort continues to recursively divide a list in half until each sublist has just 1 element. Then it recombines them, sorting them as it recombines them. So here are the steps. It'll divide the list into two equal parts, or if it's an odd number, roughly equal parts. Then it will recursively divide each part in half. And it will continue doing that until a part contains only one element. Then it will merge the two parts into one sorted list. And it'll continue to merge parts into sorted lists as the recursions unfold. This diagram depicts the merge sorts, recursive calls to divide lists in half repeatedly until each sublist holds just one element. Then the sublists are reassembled two at a time, and when they're reassembled, they're sorted. You can see in this slide, we have 1, 2, 3, 4, 5, 6, 7 single elements. So one's going to be the odd one out. That's 305. 305 gets assembled to a sublist of 305. 65 and 7 get reassembled to a sublist of 7. 65, notice it's in ascending order. And then if you go down one level, those two sublists, 305 and the sublist that has 7 and 65, get assembled to a sublist that has three elements, 7, 65, and 305. And I'm just focusing on the left-hand side of this hierarchy. Right-hand side does exactly the same thing, except it has no, at the very lowest level, it has no single element sublist that get assembled to a sublist with itself, as 305 does, because there's an even number of sublists on the right-hand side of this hierarchy. Here we have the beginning of the merge sort method, and you could see the main structure of this. If min is less than max, so as long as there's more than one element in the sublist, it will continue to recursively call. Min and max will be the same when you get to one element. It splits the list in half. It specifies min plus max divided by 2, integer division. If it's an odd number, it'll take care of that. And then calls merge sort on min to mid, the left, and then merge sort mid plus 1 to max. And so it's recursively calling itself on each sublist. And then when those recursions stop, when they end, it's going to merge them one level at a time. I really need you to take a look at this code, play around with it. The merge function is rather complex, so and it's multiple pages, so I'm not going to walk through that here. It's pretty straightforward, but it is detailed. I've taken the merge sort, which you have in the timeline for Canvas, and I've added a few tracer elements in it so you could actually see the decomposition in each recursive call. I'm going to run it right now on that original list. So here we have the initial list. It's the names, the contacts, and then here's our initial call from main to merge sort, and the first thing it does is it separates that total list into a left sublist and a right sublist. Let me make sure you can see this. So it splits it right down the middle. Now there's 7 elements, so it's going to take 4 and 3. And here's our left sublist, and here's our right sublist. And then it's going to recursively call itself on the left sublist. So our left sublist then gets broken in half. And it has a left sublist and a right sublist. And our left sublist will be called recursively, will be passed recursively. And then the right will be called recursively, and it stops when it gets to 1. And then we're going to go back to the original right sublist, which had 3 members, and it'll be passed recursively. And so it'll break it down into Smith, Phelps, and Grant. Smith and Phelps will be broken down. Notice Grant was already at 1, so she's not, that sublist is not passed recursively and then the merge method merges them all together one layer at a time in sorted order. Now, it's really important that you download these files, run the merge sort, and understand how this works. It is really important. And as you might have guessed, there's going to be an assessment for this part of the course. So anyway, take a look at those files. Don't just say to yourself, I understand this. I've watched the demo. That's not going to work. As you probably guessed, we're now going to start comparing the different sort algorithms to determine their efficiency. The selection sort, the insertion sort, and the bubble sort use different techniques, but they're all O of n squared because they're all based on a nested loop approach. In quicksort, if the partition element divides the elements in half, important aspect, each recursive call operates on about half the data. So when we partition the elements at each level is O of n. However, the effort to sort the entire list is O of n log n. So depending upon how the partition element is chosen, the quicksort could deteriorate to O of n squared. Once again, I want to stress that is if the partition element is poorly chosen. Let me now introduce two terms: quadratic sorts and logarithmic sorts. The insertion and bubble sorts, our selection, insertion, and bubble sorts fall into the category of quadratic sorts. They use a nested loop. The quicksort and the merge sort are logarithmic sorts. Merge sort, if you recall, divides the list repeatedly in half, which results in the O of log n portion. And the act of merging is O of n. So the efficiency of the merge sort, which is similar to quicksort, is O of n log n. Before we finish this discussion, we're going to take a look at another sorting algorithm, the radix sort. And it only works when a sort key can be defined. We use separate queues to store elements based on the structure of the sort key. So one example would be to sort decimal numbers, we'd use 10 queues, 0 through 9. However, in the example we're about to demonstrate, we're only going to use digits 0 through 5 to keep the example simpler, and we can expand that to include all digits if you'd like to after that. As I mentioned earlier, for this example, not the coded example, we'll demo hands-on, or live, I should say. Well, it's live when I'm doing it. It's probably not live when you're seeing it, but anyway. So for this example, we're going to limit our numbers, our integers in the list to those that contain digits between 0 and 5. So we're going to need 6 queues to sort these 10 3-digit numbers that are artificially suppressed below any digit or with any digit greater than 5. So you can see how this works. We have digit 0, digit 1, digit 2, digit 3, digit 4, digit 5. And we have them sorted, if you will. I should say arranged because this is not sorted. Arranged so that all the numbers with their first position being a 0 in digit 0. Tens position 0, 100 position 0. We don't have any hundreds position 0 because that would really be a 2-digit number. So take a close look at this before we take a live look at the slide. I'm sorry, at the actual program. Before I show you the coded implementation of the radix sort, I thought it would be useful to go through a little simulation so you can see how it sorts numbers. So to sort a list of numbers, base 10 decimal numbers, obviously. So if we have 3 digits, if the largest number in the list is 3 digits, we're going to need 3 lists for digit 0, which is the ones, the tens, and the hundreds. And like I said, before I even show you the code, I'll walk you through this, and then I'll use this example to explain the code. So the first thing it does, it takes each number in the order that it's given, and it looks at the ones or 0 bit or digit, and it places that in the first list in a position that corresponds with the digit, and I'll show you. So 100, the ones digit is 0, so I'm just going to grab it. I'm leaving a copy of the original list up there just so you can reference it, right? The next element, 54, the ones digit goes in the 4 container, if you will. 355 goes in the 5. 102, 2, 43, 3, 10, 0, 287, 7, and then 5 goes into 5. Okay, that's the first pass it takes. Then in that order, it's going to go through, and we actually have 2 linked lists in order to do this. One that's kind of a temporary that we move them into, and then we write them back into the list each time. So then we'll take these by the tens. Okay, 100, tens is 0, 10, tens 1, 102, 10, 0, 43, 10's digit is 4, 54, 10's digit is 5, 355, tens digit is 5. 5, tens digit is 0. 287, tens digit is 8. Now, in the order that they were placed, we're going to examine the third digit, which is the 100ths. 100 goes to 1. 102, 100. 5 has a 0. 10 has a 0. 43 has a 0. Hey, look what's happening. 54 has a 0 in the hundredths column. 355 has a 3. And 287 has a 2. And now we add them back to the original list. I wish I would have done this in a more tabular way. 5, 10, 43. Sorry, I'm not keeping them aligned, but you're getting the idea, right? Hey, if I were writing this on the board, it wouldn't be this neat. You see, I can grab 2 at a time. 100 and 102, 287. Obviously, the computer does a better job. 355. So they get moved back to the original list after the third pass for 3 digits. And there you go. That's how the radix sort sorts. Now we'll take a look at a coded example. Okay, now I have a coded solution here. And here is the list to be sorted. Notice it has 4 digits. Well, I'm sorry, the maximum of 4 digits. And that's put in an array named list, an integer array named list. And that's where it will reside when we're done. But we're going to use a queue of linked list integers to kind of dissect, decompose that list, and then put it back together. So here we are. Here's our queue, 10 elements. And for each, we've got this this for loop that runs a counter named digital val, or digit val, from 0 to less than or equal to 9. And then the queue at each index will create a new linked list, integer linked list. And then, well, let's just walk through this. I'll run this. I've got a couple of breakpoints in it. So let's look at our variables. We haven't created we haven't. Yeah, we did. Here's our digit queue. We haven't put anything in it yet. I forgot where I put my breakpoint. Yeah, it's been created. But here we are. We're going to start filling it. Let me make sure we can see this. So step into this. And if we look at the digit queue, they're empty. And now we're adding a linked list to each element. And that's all this first for loop does. Okay, now we're going to start at position 0 and go to position less than or equal to 3. That's an outer loop. And then the inner loop, we're going to scan from 0 to less than the list.length. And this is where we're going to identify the value of each digit. Okay, so we're going to use this temp variable to hold the value as a string from the list. Digit is going to be used to determine the character at position 3 minus position. So remember, we're in a zero-based numbering system, so we got 0, 1, 2, 3 for a 4-bit or 4-digit number. That would have to change for others. And then once we determine what that digit is, right, we're going to go to digit queues at that index, and we're going to add that element as a new integer. Remember, it's a linked list. So let's take a look at the first element, 7843. So we should be adding an element at number 3 the first time we go through this. Okay. So temp, if we find temp here, temp holds 7843, digit holds 3. Okay, that's the 3 in 7843. And now we're going to go to digit Q sub 3, and we're going to put that integer in that list. Remember the buckets I had in the demo just previously? So here we go. 3 has an element now. Its size is 1, and there's the number, 7843. So now that I've shown you how this works, right, we'll just keep on going. Till we jump to the outer loop. And if I look at digit queues now, right? 78 at digit 3, we have 7843 and 6543, 7,840, just like I put them in the buckets in the graphic depiction. So there they are, being stacked. We're still on the zeros digit. Okay, now we're done. So we've put all of the elements in their pots respectively, or buckets, whatever you want to call them. If we go to 1, we've got 3241, we've got 1211, right? Now this is just the first of 3 passes. 2, we got 4532, 6622, 3, 7843, 6543. We don't have anything in 4 because there was nothing that had a 4 in the 0 or 1's digit. There's 5, nothing in 6. There's 7. There's 8. We have 1 and 9. So you guessed it. Now it's going to go through and it's going to, guess what it's going to do? It's going to add them. Oh, by the way, look what, let me see. Let me just catch my breath here for a second. Yeah, list still has the elements in there. It's going to remove the elements. So if you look at list, okay, and now they're back in ones, twos, threes, fives, 7, and 8. See them? So it replaced the original list with the list from digit queues. Now guess what we're going to do again? I'm sorry, it was removing elements from digit queue and putting back in the list in that order as it removed them. So here we are again. Okay. Now we're at digit 4. So let's just watch as we put those elements back in the digit queue based upon the value of their tens digit. Here we are. And if we take a look at digit queues, we have nothing in the 0. We have 1,211 in the tens, right? Oops, sorry. 6,622. So you get the idea. I mean, this video is going to be an hour long if I do this continually, but that's how it manages those buckets. And ultimately, it's going to then put them, when it gets to the end or the 4th digit, they'll be in the buckets in the right order, and it will just simply remove them and put them back in the list. Let me see if I can put a breakpoint here and get to it. Let's see. So here we are. There's our list, and it's now sorted. And digit queues is empty. Obviously, I want you to download this code and run it. Make sure you understand how this is working. And I'm still contemplating the assignments for this chapter, so this could be one of them. Hey, thanks for watching. Here we have the relationship between the radix sort, the linked list, and the queue interface. Also the sorting class. Next and last topic, I believe, is comparators. Instead of implementing comparable, we can compare two objects using a comparator object. And that comparator object can be passed into a sorting method to determine the order of the sort. The comparator interface only has one method, compare, that operates like compare to method of comparable. Here's an example of how we can use comparators. Let's assume we have student objects, and we want to sort those student objects based upon various parameters. We can create multiple comparators. A comparator that compares exam scores, and another that compares assignment scores, and then the student objects are sorted based on which comparator you provide for the sort. The student class doesn't have to commit to any particular sort technique, or comparison technique, I should say. Hi students, this is our comparator demo. First, let's take a look at the student class just so you know what we're dealing with here. Here's our student class. We have some data, ID that's a string, an exam average that's an integer, an assignment average that's an integer, and an overall average that's an integer. It's pretty straightforward. Constructor, a method that returns an integer to get the exam average, get assignment average, get overall average, and the toString method. Pretty straightforward. So, and then we're going to create, or I've already created, 3 comparators. We're importing java.util comparator, and this is the assignment comparator class, which implements comparator, and we're using the student objects. So we have the compare method, student 1 and student 2, and all we do is we get their average, get their assignment average, and then we pass them to compare to, and we return the result. We also have an exam comparator that only has the compare method, and the overall comparator that will compare the students based upon their assignment average, exam average, or their overall average. So where's our demo? Here's our demo. We're just going to create an array of new student objects, and we're adding them: Mary 9775, James, etc., etc. So wait a minute. Okay, yeah, the overall average. Yeah, the overall average is computed. Got it. Sorry. I didn't take a close look at that. Sorry, let's just pretend we're in a classroom and not everything is perfect, because I don't want to go back and rewind and have to do this slide again. So here we are in the demo, and we're just simply going to do a for loop, print all the students, and then we're going to call arrays.sort, and here we go, new exam comparator. Arrays.sort, new assignment comparator, and in between we're printing out the entire list. And arrays.sort, new overall comparator. And we're just going to print them out, all the students, and I've got a run rate here. So here's the original: Mary, exam average 97, assignment average 75. That's calculated 80, 80, 80, 75. So you got Mary, James, Mark, Jolene, and Cassandra. So after the first sort by exam average using the exam average comparator, we have them sorted ascending: 75, 80, 85, 95, 97. That's Mark, James, Cassandra, Jolene, Mary. And then sorting by average, by assignment average, we have 75, 75, 80, 85, 94. You get the idea. Okay, I know this video is getting really long, and I apologize. I will put these files in the timeline for all the source code files for chapter 18, and you know what my suggestion is. You need to download these and understand how this works, and I'm still in the process of compiling which assignments I will or which programming assignments you'll have for this chapter. So know it all, understand it all. Thanks for watching. Have a great day. Sorry this video is so long.